All right. Welcome back. I think a few people are still arriving a little bit here. So as you come in, if you have questions, just let us know. As always, what we're going to do is try to start off, answer some questions that were out there from before. If you weren't able to respond to Karen's email and you have questions, just feel free to let us know. What was that question that Bill had?
So, Bill, are you on with us? Bill's question.
I'm here.
Hey, welcome. Thank you for your questions. There's some good ones. So your question was about the winch activity 125.
Yeah.
Whether the simulation was an option or you should use the actual build. Certainly, what the simulation does is somebody's gathered the data and they have put that into the worksheet. So all the kids have to do is crunch out the result from that.
Okay.
Practice with power. The thing I like about the build is, one, is experience with VEX, which they need. This is the first time that they're going to be building with motors, because all their other stuff hasn't had motors yet. So it's a nice little introduction to a button, the push button, the button switch, and the motor. I like that for my kids, they haven't done much breadboarding because we did the simulation on the electricity. So for them, it's an opportunity for them to have a purpose for the breadboarding and really figure out how to take it from the power source to the button, from the button to the motor, from the motor back to the power source. So it's kind of an opportunity for them to build a circuit that my kids haven't had. So I like that piece of it also. I have my kids, my unit 1-1 test, when the kids who finish early, I have them start building the winch. And so I tend to have a spread on how long it takes kids to take that test. And so that gets the build started because I really have one winch for every 4 teams. And then as other people begin to finish, they start taking apart their compound machines. And so I have, it's tear down your compound machine day, build your winch day. And so it just kind of all goes hand in hand while one kid's taking the machine apart and another kid's putting the winch together. So I don't mind the time of it, and for me, I think it's worth it if you've got the time in there, because I think there's some extra practice in there for them.
Okay, that makes sense. My only challenge is that I only have 6 students in POE.
Okay.
So I have one in particular that I'm dealing with that he's fairly disengaged, but the other students do fairly well, so I'll probably look into doing something like that.
Yeah, I'd probably have it in teams of 2. I just do it because of the amount of supplies I've got.
Right.
So I just butt him up in 2s if you've got that, or if you really want to save some time, you don't want to do the simulation, build one yourself and actually run the lab, but don't have them build the winch.
And that might be something I also look into doing. My other challenge is I teach IED concurrently during the same period, so it makes me kind of the commodity in the classroom.
Right. Well, and so maybe you could build that, hand that to the 6 of them, and have the 6 of them work that lab together, or build 2 of them, have 2 teams of 3, however you want to do that.
Yeah, I may look into doing something like that. That makes a little bit more sense and still gives them hands-on.
Yeah, it's a pretty quick build.
Yeah, there's good instruction pictures to follow there too, so even the students could, easily follow along and be able to complete that.
Okay, I'll look into that. Thank you.
One thing you want to make sure is that the weight that they have, they've asked them to build 2 weights. Make sure that the 2 weights are significantly different in mass. So the model that they have is 100 grams. If you build that exact model they have, it's 100 grams. I would make the other one at least 300 grams. So that otherwise, if they're too close together, you don't see any difference in what happens with the motor.
Okay, that makes sense.
That'd be my recommendation too. Bill's second question was about 1.3, and which which labs we do. I do the solar car lab, which is 131. I talked through that. That's the fuel cell and solar one. And then I think both Adam and I do 134, which is the heat boxes. I have the commercial heat boxes, and Adam has the self-built heat boxes. Same deal. It just used to be they sent you instructions on how to build them instead of selling them. I like both of those. I have been running a drafting unit that I kind of input into my kids, and we've been testing the insulation while they've been doing this drafting unit. So I've got all that data pulled already, and so on Thursday they're potentially going to start that. So both of those are good. I personally ordered an infrared thermometer so that I could do Adam's, one of those video links that Adam showed us where they had the piece of metal and the piece of book or wood or whatever, and asking the kid which one was warmer and which one the ice cube will melt on faster. So I ordered it, and I got it for like $45. So
yeah,
I'm
you can
going
get
to do
the pretty
that
cheap
lab.
ones.
Yeah, I'm going to do that lab on top of the other ones. So I thought those were that video was awesome. So those are the ones that
that'll help.
Okay, let me see who's here so I can see if anybody else who asked a question is with us. I don't think anybody else who asked me a question online is with us tonight. So does anybody have a question that came up with one after I sent that email or didn't get a chance to respond?
I have a question real quick, Karen.
Sure, what's that?
I noticed when we do the wench project, we talk about breadboarding, but I didn't really notice anything instruction-wise that gave me more information about breadboarding. Is this just like a small introduction and they're talking about it more later, or is that something I'm going to have to fill in myself?
Did you do the physical or the simulation electricity lab?
We did the...
For 1, 2, 3.
Yeah, just do the sim. If you go to the physical one of those, it's got a breadboarding video or PowerPoint that's really good.
Oh, okay, that's probably why I missed it.
Yeah, so go into that, look over that, and YouTube has some great breadboarding videos. And so one of the things that I have my kids do is I have a critique, like a video critique. And so they will, like, if they find something online that they think, hey, this is awesome, then they will write up a little critique. And if I end up integrating it into the classroom, it's worth extra credit. So saying to the kids, hey, we're going to do some breadboarding. If anybody finds a great, quick, efficient video on breadboarding, you know, write up a critique and get it to me and I'll check it out. Just because there's so much stuff out there. A lot of stuff I've seen the kids have found for me.
Awesome. Okay, I'll take a look at that. Thank you.
Adam, did you get an email from?
I did. I just sent. I
got
sent you a link.
Okay, and that when she lands, she's the one that has the question about the multimeter.
Okay.
Okay. Anybody else have any questions that they want us to talk about?
I have a general question.
Uh-huh.
I was trying to figure out what's the best way to go about grading, and how do you break down your grades for the class, and this is for the overall class. One of the reasons I'm asking is that with 155 students and you have an activity for each of them, the time that it takes to open up the file, check the work, put comments into the comment section and grade it, it's taking me at the minimum 3 minutes per assignment. So you quickly starts multiplying the minutes here. Is there a faster way or an easier way or an alternative way that you use to do the grading for the class?
I do mine similar to what you're talking about. I do all my grading digitally. Kids don't print anything off. It's all submitted via a system like the LMS. And I don't have as many students, so it doesn't take quite as much time. But I try to link it. The way I speed it up a little bit is every assignment that I have is worth the same amount of points. And then every project that we do is worth the same amount of points. Every problem we do is worth the same amount of points. So it's a little bit easier to go in and grade. You don't have to worry about, okay, this assignment's 10 points, and that one's 26, and this, so that speeds things up a little bit.
I have my kids turn their stuff in paper still, and so none of this is going to sound good to you. So I first time grade it for accuracy, every assignment, and then give them back, and then we go over them, and they get correction points. So like, say it's a 10-point assignment, 2 of those points may be correction points, or 3 of those points may be correction points, and then 7 of them were actual points for the assignment. And if I have a 10-point assignment, I may make a decision how many of those points are correction points and how many of those are straight out the gate points based upon how the masses did. So if we have an assignment and people didn't do well on it, then I'm going to make it worth more correction points than accuracy points, as long as I think it was earnest. If everybody just blew it off, then I'm not going to put it that way. It does mean that I am touching every assignment twice, because then I come back around. But of all my classes I teach, my engineering kids are the sneakiest group of human beings. And if I don't hold them accountable, like seriously, for their work, they will put such hokum down that they're just killing time. Now, it'll all come out in the wash if you make your tests worth enough. Then, so you can't fake your way through a build, or one of the building activities. You can't fake your way through a test. So if you make those points worth enough and the assignment's not worth that much, then maybe you can just grade for completion, save yourself some time, because at some point you got to balance how much time am I spending getting ready versus how much time am I spending grading, because there's a lot of prep time, and especially at the first few years you teach it, because you have to run through it yourself so many times. So maybe you grade your homework on completion for a while.
Yeah, because that's what I'm struggling, trying to balance the prep time versus the grading. And the grading, it's really consuming right now. Like, I was just trying to get ready for the beam deflection lab, because I've been jumping around because I still don't have supplies. I don't have anything. So I finally was able to get some 2x4 so we could go ahead and do the beam deflection. And so I just got that purchase. So we're getting ready to do that tomorrow. And it's just like between trying to gather supplies from wherever I could get them until I get something from the administration, and then trying to grade the papers, it's just, it's getting to be overwhelming.
You could also, put an answer key up, have, red pens out, no pencils, and, have them grade just in pen, and then when you see the paper, you look at the paper, they've self-corrected, but you know how much they had to correct. I mean, you still have to scan it and make sure they're correcting what they can, but an earnest kid is going to do what they're, is going to do what they need to do. So, I mean, that's, having them grade themselves. If you're going to go over it with them anyway, that's another kind of time-saving mechanism.
Okay.
I don't know how long you've taught, but you do get faster at it a little bit. It's still all-consuming. I still spend hours doing it. So.
Yeah, the Project Lead the Way stuff, one of the benefits of the program is that it's a really good program. One of the downsides is because of that, there's a lot more work. I know some of my coworkers that teach just Project Lead the Way courses spend a lot more time grading than I do, because I split my time between, Tech Ed and Project Lead the Way.
Did that help? Or do you want us to reiterate, or I don't know that we gave you I don't know if we fixed it.
Yeah.
I tried doing. I can't do the paperwork because we don't get much paper. We get a box of paper at the beginning of the school year, and after that I have to buy my own papers. So I opted to do most of it just online submission, just so that I don't have to print and go out and buy paper, because the budget is not there. But like I said, even doing the online grading, it takes a while, because by the time I open each file and really, if you're going to grade something, you got to give some feedback, otherwise it's useless, right? So I try to give feedback so that they could understand and learn from their mistakes. But it's just very consuming.
Yeah, and so you're gonna have to make a call on how much how much of it you want to grade on completion, and then give the feedback when you're going over it to the whole class.
Okay.
And so you can say, look, I look at each of them, but this is really where I'm going to comment on what I saw in general, and I'll make notes when I'm going through, like, I need to address this issue, and this issue, and say, these are the things I saw. And so you can make poignant comments to your kids just from looking at them and not write them all down, or type them all in. That might save you some time.
Yeah, because I need more prepping time, not grading time.
Right.
Just being the first year, I truly need the prepping time.
Yeah, and you got to make a decision which one's a better investment. And prep time first year is your better investment, I think.
Okay.
Tricia, are you with us?
Yes.
Okay, excellent. Can you see us, or are you just listening to us?
I am waiting for my laptop with, anyway, I have a problem that my link is sent to one email, and then I actually use a different computer because we don't actually put the link on the LMS, which is unfortunate. So I'm actually logging in on my other one, and I'm listening. I'm actually looking at you. You are not looking at me until my other computer.
Oh, that's fine. I guess the question is, can you see Adam? Because he's got a multimeter. He's going to kind of talk through some folks had multimeter questions, but I know that you were one of those.
Well, I did have questions, but I think I did the thing today that I had the questions on and couldn't get the damn meter to work, even though it worked when I practiced, and so I kind of crashed and burned on that. So,
what was happening that you say it wasn't working? What were you having problems with?
Well, I was reading the amps, and all of my little red multimeters, the little A and D ones, still had a little piece of tape on the back of them that said A not functioning.
Yeah.
So, so I assumed that meant that the amperage wasn't functioning. I did have one of those bigger green meters, but that was the one that I was actually able to work over the weekend. And the first two kids that I helped with that worked. And then it just quit taking readings. I don't know if I don't know if I maxed out my current. I'm not sure what happened. I wasn't sure what to expect, but I had hoped to get through more than 2 attempts before I tried my meter.
Yeah.
My guess is you blew a fuse.
Yeah, and that happens instantaneously. I mean, one time you hook it up wrong, it's just done.
Yeah, you roll it through, and it touches resistance. It's gone.
Yeah.
So you think I rolled it? I don't know it rolling.
Like with the dial, if you did one of these things while the circuit was hooked up, you went through a range that probably caused you to blow the fuse.
Okay. I'm pretty good about that.
As long as you're not hooked up, you change and then go back.
I did have a lot of kids that follow directions.
Amen.
We all do, yeah.
Whatever they want to do. Well, not whatever they want, but they had some really high weights on there, and so I don't know if that spiked the current either.
Probably not.
What happened? The last time I took electrical engineering was 1984, so I'm kind of refreshing my skills in this particular area.
So you were measuring current doing the winch activity 125?
Activity, yeah.
Yeah. When we set it up and you put on like 100 grams or you put on 500 grams, the current doesn't really fluctuate too much. It's pretty even for both of them. And off the top of my head, I think ours was somewhere around like 120 or 150 milliamps or something in that neighborhood.
I think so too. It was pretty low.
Yeah.
The kids that got a reading, it was somewhere in the 185.
Okay, yeah.
We had two different weights, and it appeared to change by about 20 milliamps.
That's probably true.
Yeah, that sounds about what I would get.
Yeah.
Give them a number and say, okay, we weren't actually able to measure it. Why don't we just say that this was the number and calculate the power from there?
Do you have a power supply, or are you using batteries?
We were just using a little battery.
Yeah, that's right. I do that too, because I can't store power. I don't have a store space for power supply boxes, so nor the funding. So so we just use batteries as well. But your red multimeters, if they have screws on the back, you might open that up and see if they have fuses that you can take out and in. If they do, just take that fuse to a hardware store, and like $1 later, you'll have a new fuse.
Yeah.
It might be that your fuse is welded in. If that's the case, I'd throw it away. Keep the
I did do that, and I replaced the fuses, and it didn't appear to work any better. So I don't know. So I did find an 89-cent fuse at the WeSupply.com. So it's not a $3 fuse.
You can buy them in bulk.
Yeah.
Cheaper than bulk.
I buy a lot of them. You need to save up and I'm saving up for these ones that Adam recommended. So
they're worth every penny.
Yeah. I just got to wait till I can.
Yeah.
I just bought an infrared thermometer, so I've kind of spent the wad for a little while.
Yeah. We integrated like 5 one year and 5 the next year until we had enough.
Yeah. It's awesome. Okay, I think that was everybody's questions thus far. So we were going to talk a little bit about, we've kind of talked through 1.3. So we're going to talk about 1.4 a little bit. Is everybody okay with that? So I guess anybody who's not okay with that, that's what we're going to do. So Adam, you want to talk through pros and cons to the activity, and then what else is in there? You want to show them?
All right. So, 1.4 is we'll call it a lesson that most of us as POE teachers are not super fond of, if you will. It's the idea behind each of these units. So unit 1, 2, 3, 4 is the students are going through a bunch of activities and then projects in order to gain the knowledge that they need. When they get to the end, the culminating lesson, which in this case is lesson 1.4, it's supposed to be a problem, like an open-ended problem where now they're applying the knowledge that they've learned in the previous lessons in order to solve this problem. And for us, if I show my screen here, this one they call a renewable energy station, if you will, is what we've always kind of coined it. And what you do is you give your students the hydrogen fuel cells, the solar panels, and if you're using Fisher Technics, you give them little motors with fan blades on them. If you're using the VEX equipment, which most of us are, then what we end up doing is you use like a motor as like a hand crank generator, if you will. And the idea is you give them certain criteria where they're supposed to go through and develop a energy station, if you will, where they're using solar, hydrogen, and the generator in order to produce as much electricity as they possibly can in order to illuminate as many LEDs as possible. So they give you, this has been an activity that's been around for a little bit, but they give you different time frames of the day, and they basically tell you that, okay, at this time of the day there's going to be high wind and no light, or this time of the day there's going to be low wind and bright sunlight. So the students are supposed to design their platform around those times of day so that they can best utilize whatever energy source that they're using. They do have you go through and look at the LEDs. There are LEDs on the purchase manual, so there's specific ones that you would go out and get. They're relatively cheap, but it doesn't really matter. If you have some, you can use really any LEDs. And they have you figure out what the voltage requirements are to illuminate a single LED or 2 LEDs or 3 LEDs. And then you're kind of, once you go, and I kind of work through with my students doing these different steps, and then I kind of let them go, and they have to kind of figure out how to best wire up this energy station in order to illuminate as many LEDs as possible. The downside to this problem, most of the problems are supposed to have multiple ways of getting there or getting to a solution or multiple outcomes. Really the best way to hook up any of the systems that we have here is to hook everything in series, so that we're adding the voltage of the photovoltaic cell, we're adding the voltage of the fuel cell, the hydrogen fuel cell, and the voltage of the hand crank generator in order to light up as many LEDs as we possibly can. And for the most part, each of the students or each of the groups gets pretty much the same answer. So this is actually a project that a lot of us kind of skip over or do as like a quick one-day activity, and then we move over and we move on to the next lesson.
It's got one of the things when we changed to VEX, you say to your kids, because what you do is you put a gear on your motor and then you have them hand crank it to see how much voltage they can get. And that, in the hands of a 16-year-old boy, is a gift. And so they will hand crank that thing like it is a contest. A, I don't love that they're doing that to my motor. B, they can produce enough voltage to kind of take care of the whole deal. And so they'll be like, yeah, I'll just, my wind turbine will, take care of this. And I also run into some trouble that the electricity doesn't always flow the direction you want to because we don't have diodes in our system. And I don't do it. But 1.4's got some other stuff in there that you need to look at. Please don't skip 1.4. Adam, you want to get design? You want to do the design process? So there are some really important papers in this section. I think Adam's opening Intro to Design Briefs. So once I get to section 1.4 or the equivalent for it, I personally, the University of Kansas has a poster bridge competition, so my kids replace the big project where they introduce the design process and design briefs and decision matrix, all things we'll show you here in a second. My kids use all that with the design brief, and so, or with their poster bridges. So if you have some engineering competition near you or some really cool problem, you can do that with this as well. One of my friends uses the solar power cars for her big design challenge, and they have to go through the design process for when they're building their solar power cars, and so she kind of uses that. So can you pull up the design process?
Yeah, I think that's back here though.
Is it not in here?
Yeah, if it lets me open it up.
Okay.
Design process should be under your general student resources.
We have had kind of multiple versions of the design process, and now currently all of the Project Lead the Way classes use the same design process, which is awesome. So they'll run through the fact that there are 2 or 3, there isn't a universal design process, but that we are going to choose and go with one in Project Lead the Way. So they show 3 or 4 of them. This is our old one, this 12-step. Yeah. This is the one we currently have is the 6-step, which I like. The 12-step was a little too micropic in between the steps, but I like this one. There is probably, I don't know, Adam, what do you think, at least 2 questions on the final that ask about the design process.
Yeah, like, typically they give you some sort of scenario and say, you've just done this, now what's the next step in the design process? And they have to be able to select, one of these specific steps.
So they need to have those 6 steps memorized because they need to know what those are, and those are not on the formula sheet. When I get to my projects, once I've introduced this to them, my projects are broken down on their rubric. Like you need to have steps 1 and 2 done by this date, and then steps 3 and 4 done by this date. So then when they come up and show it to me, they have to write out step 1 and write that down and say what it is, because they need to know those 6 steps and what's in those 6 steps. Back in Define the Problem is that design brief that Adam ran through, and that's a way to formally write up and state the problem, who's involved in it, and what the constraints are. So that's in Define the Problem. And then we get to step 2, Generate Concepts, and this is where you see Decision Matrix, and Adam will open that up for us. You want to talk about that, Adam? Or?
Yeah, there is a whole specific PowerPoint that goes along with this. It's also located underneath the general student resources. Excuse me. But we do utilize this, and the students get it in IED. But basically, when we get into a problem, the students have to come up with a way of showing us that they chose the correct pathway, if you will. So they create this chart, basically, we just call it a decision matrix, where they have a whole bunch of their brainstorming ideas. And for my students, it could be anything like maybe it's just one component of a project that they're trying to design, or it could be the entire concept of what they're doing. And then they come up with some criteria and they rank it and basically figure out, okay, I'm going to choose idea number 4, not because it's the one I designed, but it's because of, this criteria that this is the one that we should go with. And typically with the students, I don't have them have like 6 ideas. I usually say, 3 to 5. They come up with 3 or 4 different ideas, and then they usually have somewhere between 3 and 5 different criteria for what they're selecting in there. And that, again, just like Karen was saying, this is part of what my rubric. They have to have a decision matrix as part of this, and they have to be able to utilize it.
For my kids, I tell my kids that they each have to have independently 3 brainstorming ideas, and then when they come together, I assume they'll have at least 4 that are different. So they have to have at least 4 options on their decision matrix, and then I say you have to have at least this many criteria. And so otherwise they won't. So if you don't put a minimum on that, they will choose the minimum. It's like, yeah, we had 2, and we based on these 2 things. And so, but I have them brainstorm independently, and then come together with that to get that decision matrix. But it's my kids who are in engineering school at college and grad school, in their senior projects, they have to show a decision matrix. So I thought that was pretty cool to know that they're still using it, because I've had like talk about the template that they use, and it looks just like ours. You'll notice in the design process that it gives the ability to wrap back around. So you develop a solution, and then you're like, is this good or not good? Oh, if it's not good, we're going to go back up and generate some more concepts. You come through, you make a prototype. Did it work? Did it not work? Oh, if it didn't work, we're going to come back up, and maybe we need to go all the way back up and look at what the definition of the problem really is. But this they need to, if you want them to do well on the test, there are probably 2 questions where they need to know the order of those, what comes within those, and what does next. And so we talk about them constantly. I took a picture of the slide and took it to the library, and they made a big poster of it for me. So it's verbiage that we use all the time.
And that was a question that I was going to ask, is does Project Lead the Way have like a poster that you could order? Because I would be interested in putting one of those in my classroom.
I just made one. I don't know.
Yeah, I'm not sure if they have one to actually print off. But yeah, in that PowerPoint, you can easily grab that chart and print it off large scale.
Yeah. So there's some good stuff in 1.4. So even though Adam and I don't do that specific lesson, we do talk about the stuff that's in it and use that stuff. After my kids have seen the design process and the design brief and the decision matrix, there is no time that they don't have to use that and denote those 6 steps within their notebook or to me for full credit on any project that we do.
All right. So that takes us through Unit 1, and I know that we might be a little bit ahead of where some people are at this point, but what we're going to do is start off on Lesson 2.1, and then for 2 weeks from now, we're going to do the actual Trust Calcs part of it. Basically, that's our night, is going over Trust Calcs, because it's probably the hardest thing that you're going to do with your students, is getting them to grasp that concept and be able to solve the Trust Calcs.
We have one individual who has already done Unit 2. Are they with us? They jumped to Unit 2 right out of the gates. Okay.
We'll keep tab. the juniors. Yeah, because you don't want them to have it. Because it's one ring. You gotta share it.
All right.
You gotta share it with everyone. You gotta
I
share
don't
it
think
with
that's a question for us.
I don't either.
Yeah, always there.
I don't either.
All right.
Okay.
It's basically a ring that goes on 24/7 constantly.
Figure out who that is. Okay. So what we'll end up doing here is we'll start off with lesson 2.1 in statics. Go over centroids and beam deflection, and then I'll transfer it over to Karen, and she'll finish up with 2.13 and 2.14, and then we'll kind of hold off to the other stuff until we get back in 2 weeks, just so we don't give you too much in one night. So we basically move out of energy and power here, and we start to look at structure and shapes and materials, and how the structure or the shape of the material or the actual chemical makeup of the material is going to affect the overall performance of something, and how we design things in order to be stronger based off of position and shape and material. So one of the first things they go over is something called a centroid. And it's actually, I think it's kind of a fun activity. I think for the most part, the students enjoy it. It's essentially a 3-part activity. One of the first things I would do is I kind of introduce the concepts via the PowerPoint with centroids. We talk about, what a centroid is, and it's essentially the theoretical center of mass of a 2-dimensional shape at this point. And they go over a couple of examples at first. And since we're really going to be looking at beams that we would use in order to make structures, we're kind of looking at similar shapes that we would find beams in, and we're going to end up taking what we call the cross-section view of it. So essentially you're just looking at the end of it, or you're slicing it and looking at the 2-dimensional shape of it. So they show you, like here, if there's an animation, it would show you this turning, so it'd be like an I-beam. And then they go down through, and we do some review, because most of the students should know how to find the area or the center of a square or a rectangle. Same thing with a triangle. If not, it's a good review for them. They give you this formula, which we will use in the activity, so I always have the students write it down. Basically a formula to find the centroid location of a semicircle or a half circle. And then you get to this slide with them, and they all go crazy, and they're not too happy with you because there are no numbers on this page right now, and these are the formulas, which can tend to be a little daunting for, especially I have like 9th grade and 10th grade students for the most part. But you calm them down, and you kind of break it down into each little step, and you find out it's really not that hard. It is a little bit tedious, but it's not that hard. So essentially what we find out is it's pretty easy to find the centroid location for like a rectangle or a square or a triangle. But what happens when we have a more complex shape like this? It's not so easy to find where that location would be. So what we end up doing is we use this, we find the centroid location for each of the individual shapes, and then we use one of these formulas in order to basically average the 3 shapes together and find the centroid location for the overall shape. So they step you through in how to find that, and it does a really nice job here. I have the students go through and they create a chart just like this, where they have all the different shapes and they have the different areas and the different measurements for them, so that they can very systematically go through and solve for the centroid locations. So we go through this, they get exposure to it at first, and I would say it's not very concrete at this point. It's not very, they're not very good at this point because they were just exposed to it. So what we end up doing in the activities, the first 3 problems give them a chance to practice that stuff again. So they go through, and you can see there's a chart very similar to the one before, where they break the shapes up. But then even just besides doing the math, what we end up doing is we have the students create a shape. And we're going to use a typical beam shape, like an I-beam or a T, or even a box or something to that effect. And what I have them do is just use cardboard to do that. So there's a couple of examples I have here of just some simple cardboard cutouts that they use. And it doesn't really matter what size you have, if it's a 4-inch by 6-inch, or if it's 20 inches by 30 inches. it doesn't really matter. But what they'll end up doing is create that shape and try to be as even as possible. And they'll pin it up to the wall so that the actual shape will balance itself. And then what we do is we take a string with a weight on the end of the string, hang it from where it's being pinned, and just trace over that string. You can see right here is a line from us doing that. Then what they end up doing is pin it at a different location, put the string from the pin down, and then they trace over that. So you basically create like a plumb bob, and gravity holds it straight down, gravity pulls the shape, it balances it out. And what we'll end up finding out is if we do that in 3 different locations, those lines are going to cross over each other, and then right there is where the centroid of that shape is going to be. So we gave them the mathematical way of figuring it out. Now we give them a physical way of figuring it out. And then what's kind of cool is the students will put the shape on their finger, and they can balance it at this point. So it gives them a real world hands-on version of it, if you will. At the end of the activity, the third part of this is that they get into a program called MD Solids, and they actually will draw up the shape that they created in MD Solids, and then they'll hit compute, and it does all the math we just took 45 minutes to solve in a second. And they're going to verify their results from the shape they made on MD Solids. So if I open that program up, this is what the program looks like when you first open it up. There's a number of different things we're going to use. Eventually we'll use trusses and determinate beams, but right now we're going to use this one called section properties. And then if, for example, I had, what was that? I think it was an I shape there before. So I can go up in here to flange to I shape. I can put my measurements for whatever that was, if you like metric or inches. And I don't know, let's just say that this was 4 inches here and this was an inch. Make that 3 inches and make this an inch. And then we can hit compute, and what it'll actually do is it'll solve for our centroid location right away, and we can change the different properties here if we need to. It also solves for some other things that we're gonna do in a little bit here, but basically right now all the students are doing is checking their math to make sure that they measured properly and that it balanced properly. Oops. One other thing that if the students aren't quite getting the concept of the centroid yet, they're going to get it after they play this game.
Centroid Master?
Yeah, if you go up to the animated learning tools, and on the left-hand side, there's a game called Centroids Ropes, or Centroids Learning the Ropes. And if you open that up, it is a game. I forget if it was created by a different university. I feel it was like the University of Michigan or something like that effect. And it's freeware, so you can go online and find this. So if the students don't complete this during the school day, they can do it for homework as long as they have internet connection. But basically it takes them through 6 rounds, and it has them just guess. So they place a centroid here, this little marker for the centroid, and it's not right. So they're saying, is the center of this shape really above or below that? So they go through and click it. If they get it right, they get 25 points. If they get it wrong, they don't get any points, but they go to the next shape. So I'll just click through here quickly. The beginning is pretty quick, just above or below. And what ended up happening is after each round, they're going to get a score out of total possible points. When it gets progressively harder, where they're starting to having to choose incorrect answers, and then all of a sudden put in the values of different answers, and then in the very end, they have to do the whole entire calculation and just put in that one answer. What I do with my students is whatever the grade is at the end of 6 rounds right here, that's their grade on the assignment. So if they want 100%, they can redo it 1,000 times to get 100%. And it makes it really good. When they're done this, they have the concept. To get 100%, they really have to know what they're doing.
I use the one right below it, the Centroid Master as my assignment. My kids do this as the assignment the day before Thanksgiving break. We come to school on Tuesday, but we don't have school on Wednesday, and so I have a mass amount of students who are gone. And so they can do this. Kids can get MD solids for 30 days for free. And so they can do this at home, and then they can just print out the certificate that's at the end, so they don't have to do it in your classroom. And, you know, I say you can do as many times as you want, but you have to have a score of 90% or higher or whatever. So I will tell you that both Centroid Ropes and Centroid Master have an occasional mistake in them. So if your kid gets into a mistake, what I ask my kids to do if I'm there is to show it to me. If I'm not there, they just take a screenshot of it and show me what it said, that said it was wrong and it really should have been right. I can't track it enough to figure out where the mistake is, because it's pretty rare.
Yeah.
But just if a kid tells you that there's a mistake, you might walk over and take a look at it, because it might be. But this is by the time they're done with those, and they play them. Like, my kids will just play them because they think they're fun. So so it's a good way to have something to do in class. If you're gonna be gone or they're gonna be gone, it's a good way to get an activity in. And everybody knows how to get this, or does everybody have this? Because it's free. You get a free year of free action set of this.
Yeah.
To Project Lead the Way.
So you just kind of dove into the Centroid, 1.1 or whatever, or 3.1, whatever the first item was. Is there an overview of the unit? I guess it would accumulate in a big bridge project, but I guess one of the things that I have trouble with is when I kind of bog down on some of the calculations for some of the smaller things, my kids have a hard time seeing the big picture.
Yeah.
And I get a lot of, oh my God, this isn't just another math class. And they kind of need to see, like, kind of where we're going with all of this. So even with, like, the electricity, I explained, we're going to do it in a simulation, and then we're going to build a winch, and then it's going to turn into a car that, so that I find that they kind of need to see where they're going, or they kind of set down their bags when they get to the first hard thing, and I get some static.
No, I mean, that's a good point to make. What I usually like to talk about for this lesson is the fact that, our end goal here is looking at trusses, and how do we design really strong trusses, and how do we figure out, which member needs to be larger, which member needs to be smaller, and how do we do all these different things. So, this component, we're just looking at, okay, where is the center of this shape for this beam? And we're going to find out that the center of the shape of this beam is really important, because at that point, when we do beam deflection, we're going to find out there's really not any force there as far as tension or compression. And then we can use that in order to figure out how to make the beam stronger. So it's kind of like I try to connect it to trusses. Okay, well, how does this connect to trusses? So I connect each little chunk to that. There isn't a overview PowerPoint. There is a PowerPoint that we used to actually do first, but now for some reason the curriculum it's bumped back 2 lessons, I believe, or 2 things. Yeah. So I mean, you could easily do it first, and it gives a bunch of those basic concepts.
The intro to statics.
Correct.
And it's, I think, in 2.3 maybe. 2.1.3, and I do it. I start that way.
Right here, this introduction to statics. Yeah, for some reason it used to be number 1, and they bumped it down the line here, but okay. So when you get through the centroids, the center of mass, basically, then we look at beam deflection, and there's a presentation and there's an activity. So what I do first is I kind of have like a little demonstration in front of the classroom where I take different size, like dowel rod essentially. I'll take wood dowel rod, I'll take a rod that's made of aluminum, a rod that's made of plastic. I have some clear acrylic plastic, and they're all about 3 feet long. And what I do is I support them at the same distance apart, maybe it's 2 feet, and I hang a weight from the middle of them. And you find out that the different rods, even though they're the same exact diameter, they're going to bend differently based off of their chemical makeup. And what we end up finding out is it's something that we call the elastic modulus or modulus elasticity. So then we kind of talk about, well, if I apply 5 pounds to this one and 5 pounds to this one and 5 pounds to the next one, I can predict how much they're going to bend. And I can use those predictions in order to design structures. Or in this case, we're going to use that amount that that material bends in order to tell the class how much a student weighs. So a student will actually stand on a 2x4 in our activity, and based off the amount of deflection there is, we're going to tell them how much they weigh. And it's really dang accurate. It's pretty dang close. I'm usually off by maybe a pound or less, maybe 2 pounds on a bad day. So we go through and we talk about the different makeups. We get into what's called moment of inertia. And the fun thing about moment of inertia is we use this formula, base times height cubed divided by 12, and we end up getting a unit of inches to the fourth, which for most of the students doesn't really make a lot of sense. But basically it's just a way that we can compare a shape's ability to not want to move, if you will. So the higher moment of inertia is, the more it's going to want to resist this force. So they go through, we do some moment of inertia calculations on rectangular shapes. We look at the difference between position. So if we have a vertical position of a beam that's a 2x6 versus a horizontal position of the beam, we have a significant difference, and in fact it's like 14 times different just based off of position and amount of material. So we can stretch that a little bit further and get into different shapes. We can look at right here, we have a 2.5 by 9.5 tall rectangular beam that's using about 23.8 inches squared of material, and our moment of inertia is 178, where this one's using less than half of the material, and our moment of inertia is greater than half of this. So it ends up being that we can have a much stronger material using a lot less area here. So then they finally get into the actual chemical makeup, where we get into modulus elasticity. Students apply the formulas, and we get into what we call beam deflection, which is this formula that we're going to use here. And really in this example, the only thing that we have different here, we have two different beams. One's made of wood, one's made of plastic. They're exactly the same length, exactly the same moment of inertia. The modulus elasticity is the only thing that's different here. And based off of that, we're going to find out that there's a significant difference in beam deflection. So we go through, do the calculations, and we find out that there's, it's significantly greater, that the beam that has the lower modulus elasticity is going to bend easier. It takes less energy to bend that material. So in activity 2.1.2 with the beam deflection, first thing we do is I would recommend going and getting a brand new 2x4 or a 2x4 that's as straight as you possibly can get, has as few cracks and knots in it to make this activity work a little bit better. I have the students measure the beam with a dial caliper, so they're down to the thousandth of an inch. And then we'll do our moment of inertia calculations for the vertical or horizontal position of the beam. Then we stand, I used to stand this between two different tables and have a kid sit on it, but that didn't work out as nice for measuring. It's kind of an awkward way of measuring. So then I had just two cinder blocks on the ground, lay it across two cinder blocks, and the student stands in the middle, and we just measure from the floor up to the bottom of the 2x4 to see what our distance is. Once the kid stands on it, we see how much it deflected, and then we get our total deflection, how much different it is.
Do you do it just for one student, or do you break it into groups and each group gets a chance to do it, or?
Typically, I do it as a class. So we'll have one student stand on it that we know their weight. We use that information to calibrate the beam to get its modulus elasticity, and then we get a second volunteer to stand on it that we don't know their weight, and then eventually we figure out down the road that it is. I know other people that worked with in the past that they do, 2 or 3 groups in the classroom and have it do. For us, it kind of speeds things up a little bit. I don't have to have as much in supplies and room, and it gets to be a little bit more chaotic.
And one part of this, you take the beam from joist, or from plane to joist, and it would make me nervous not to be present when my kids were standing on that. It's a little wibbly wobbly, and you got somebody standing on it, and so I don't know that I would want too many groups doing it without me supervising, because certainly they could tumble off.
All right, so yeah, so they do all the ones up above here are horizontal with it being flat, because it bends a lot more, so it's easier for the students to measure or see a difference. And then the very last one we flip it up vertically here, and then you don't get as much of deflection. We usually get something like 1/4 of an inch, or not very much deflection when it's in the vertical position. And then in the very end, they get some fun times, get some practice here of just doing area calculations, moment inertia calculations, and then figuring out what the beam deflection would be based off of the input given above here. One of the biggest things that they do here is the students will put in 12 feet into the formula instead of 144 inches, and they'll get an answer down here for beam deflection that's like 0.00000. It's too many zeros. It shouldn't be that small. So that's right away, if you see that down here in the bottom, you know something went wrong.
You can do this, and I have a 50-minute class period, and we can do this easily in that time as a whole class. And they stay pretty engaged. I have it's usually wrestling season for me, so I have some kid that knows exactly what they weighed that morning. Yeah. So I have a kid that probably knows exactly how much he weighs at that point. So. Questions over what you guys saw from Adam?
Yeah. That was a lot. A little bit of time. I was trying to get through it, so.
You guys can kind of marinate in that for a couple weeks, and we'll recap questions that you may have over that. I'll hold off talking about the next two with the three-body diagrams and force vectors for our next meeting. And then we really want to spend some time. We spend a whole day in training, so it's a pretty significant chunk of the summer training doing trust calculations. And so we want to spend some time with you guys on that. And Adam's got some nice resources. If he's got some videotapes of him doing some of them. So we're kind of trying to get a little bit ahead so that we can spend a reasonable amount of time in that, because that's one of the hardest components of the class.
Adam, can you put those links into somewhere and under the POE, because I'm doing beam deflection tomorrow because I don't have supplies, and this is one of those modules that I could do because it requires very little supplies. So
Okay.
I'm actually doing I'm doing beam deflection tomorrow, and so I'm going to be going into trusses soon.
Okay.
Before we meet again, so.
I will email the links to everyone, and I have basically what I have is a video that activity 2.1.7 is our truss calcs activity, and there's problem 4 and problem 5, which are 2 trusses that the students have to work through. I just sat through and I did a little video of going through how I solved problem number 4. So I'll put that out there, and I also have another video that I use when we're showing centroids, just as a kind of a real world, where does this apply.
Okay.
Well, it's a little after 7. I know in Kansas City it's 5 minutes until the first pitch of the World Series that we're in. So I don't mean to kick anybody off, but I'm gonna have to watch a little ball game here. So Adam's gonna send that out, and then you can always contact us and let us know if you need something in the interim. But we'll plan 2 weeks from today to come back together.
Thank you.
Thank
All
you.
right. Good luck, everyone.
Thanks.
So in a couple of weeks, we'll also outline our kind of change because we land on that Tuesday before Thanksgiving. So next week is the last lesson before Thanksgiving.
Yeah, it'll be the 10th, right?
Right.
Okay. And then we'll have to bump from the 10th to the 1st is what we're doing?
We won't do the 24th, but yeah, it'll be the 1st.
Okay.
And then come back around to the 15th. And then probably wait until the new year after that.
Sounds like a plan. We could always do, holiday week if you wanted.
Yeah.
So I don't see many people showing up.
That's right.
Yeah.
That's right. We've got a pretty long Christmas break, or winter break, excuse me.
Yeah.
Not holidays, I'm sure. But
Yeah.
indeed. Okay. Well, I'll get that out. Thanks for that. That video I was like, I need an infrared thermometer. They're like, why? I'm like, because it's so cool. So
it was really, yeah, it was pretty sweet. Yeah, what's funny is I was thinking about today, that really shows the connection to K value. But I was like, well, how do you show the connection to CP value? It's like, well, what if I did the same thing, showed the K value, and then I took them and threw them in an oven, and then brought them out, and then put ice cubes on top of that? Because now you're looking at which one holds the energy, which the wood's going to hold the energy better, where the aluminum's not going to. It's going to dissipate pretty quickly.
Right.
So that would be
just continuously, yeah.
Kind of
wait 25 minutes and then put an ice cube on it.
Yeah.
And see which one melted faster.
Yeah. It's cool stuff for us. I don't know how much the kids will find it cool.
I get a really cool thermometer out of the whole deal, so it's awesome.
Yeah.
So, okay, very good. Well, thanks for organizing it all, and as always.
Piece of cake.
We'll, yeah, I hope so. So far, so good. That was really, I think, efficient.
Yeah.
I kind of like the questions on the front end.
I agree.
Specifically answering them, I think that's.
Yeah, because that's kind of, they need to get those questions answered, and then we can kind of give them a little bit of new stuff. I mean, heck, if all they want is just get questions answered, we could do that the whole time.
Right. No, I think it's an efficient use of time, which is ultimately. I did not see. Did you look at the chat down here?
They were looking at. Looks like they were going for trust software or something. I was looking at nothing too specific.
West Point Bridge.
I don't really understand what Tricia, what the issue is with her getting to the meeting.
I don't either.
Yeah.
I don't understand why from any mechanism she can't use that link you sent.
I don't know.
Do you?
The only thing I can think of is maybe the computer she's using doesn't have a camera or something, or doesn't have a microphone, but
anything she acts, it doesn't. But putting it on the LMS wouldn't fix that.
I know. I don't. I guess I can put it on the LMS if I remember, but the other email that she forwarded it to, I put that on the chain, so she'll get it to both emails. I don't know. We'll figure it out, I guess.
I think she's a little technologically challenged as part of it. So like when I was trying to talk her through her multimeter, I just couldn't tell what she was trying to do.
Yeah.
So
sometimes it's hard unless you can actually see it.
I know. I wanted to be like, can we Skype? Because I just want you to hold, and then I'm not sure what I would be able to even read or whatever. But yeah. No, when I saw that pop up, I was like, oh.
Yeah.
Adam's going to include her because I'm sure it's something she can get to.
And she did ask for it to be put on there, but I forgot. But
yeah, well, you're a better person. I'd be like, no, I'm going to send a link, try and figure out how to make it work.
Yeah.
You're a good person for thinking bad of yourself. Okay, very good. Well, I will talk to you next week then.
See you in a couple.
Okay.
All right.
Thanks, son.
Hey, good luck.